Hey folks, I wanted to do another example showing a more complex use of u substitution. So here's an integral from the textbook. So it's the integral of x cubed times the square root of x squared plus 1 dx. So when I look at this, the first things going through my mind, I'm looking for if there's any algebra that I could do that might be able to help me simplify this. I don't immediately see anything. So, okay, the next thing that comes to mind is a u sub. So let me go ahead and try u equals. Now, as I look at this, I like the idea of letting u be sort of the thing inside of the composition of functions. So in this case, let it be the thing inside of the square root, so x squared plus 1. Let's see what that gets us. So u equals x squared plus 1, which means du is 2x dx. And I like to always solve for the dx, so du over 2x is dx. Okay, let's go ahead and plug all of this in. So my integral now becomes the integral of x cubed square root of, so the x squared plus 1 becomes a u, and the dx becomes du over 2x. So now I'll pull out the 1/2 in front and simplify a little bit. X cubed divided by x leaves me an x squared left over, square root of u du. Now, you might get to this point and say, oh no, we're in trouble. All of my x's, haven't disappeared, right? I still have an x squared left over, which must mean that we did something wrong. Well, a lot of times that is the case, right? If we choose a bad substitution, things won't cancel nicely. But, you know, in some instances, in this instance, I think we should be a little more persistent. And let's take a look why. Take a look, for example, at the expression for u. And notice that I could almost replace x squared by u. I mean, there's a relationship that looks pretty close. So the trick here is maybe I take the equation for u and just manipulate it, right? So instead of writing u equals x squared plus 1, certainly that's the same thing as saying u minus 1 is x squared. And now this is the key, right? I have x squared in both those places, which means I can continue substituting in expressions for u, which make my life a little bit easier. So the x squared I'll replace with u minus 1, and then the square root of u is still there, and then du. So what do we see from this? We see that with a little bit of extra work, right, a little bit of tenacity, we can continue canceling out those x's, or replacing those x's with more expressions involving u. And now I'm left with an integral, which perhaps I have a better hope of solving. And indeed, now I look at this and say, algebra looks a little bit nicer here. Let me do some algebra here. This is, if I distribute the root u to both terms, I'm going to have u root u minus root u du. But that's none other than, so that's u to the, well, it's u to the 1 times u to the 1/2. That's u to the 3/2 minus u to the 1/2 du. And hey, look at that. This I can solve. So this, I can get the antiderivatives, u to the 5/2 times 2/5 minus u to the 3/2 times 2/3. And then don't forget your plus c at the end. And so if I simplify, and then let me also plug back in my expression for u. So u was x squared plus 1. So I'm going to get a 1/5 x squared plus 1 to the 5/2 minus 1/3, again, distributing the 1/2, x squared plus 1 to the 3/2 plus c. There we go. So a little bit more complicated than what we saw in class, but certainly within our grasp. Again, this goes back to the idea of, try something and, be tenacious in your ideas, right? I mean, we hit immediately a little speed bump, but with a little bit of thought, we were able to get rid of that leftover x squared by manipulating our expression for u. Okay, I think you'll find this helpful in your first homework assignment. Okay.